Almost everything that moves, spins, or rotates in our world depends on this unsung hero. It's a component that's always fighting a silent battle against friction. And honestly, without it, our machines would just grind to a halt. So today, we're going to dive into the hidden world of the bearing. Okay, so let me just kick this off with a question for you. What could possibly connect a massive 1,000-megawatt hydro generator, we're talking something powerful enough to light up a city, with the incredibly delicate high-speed gantry of a medical CT scanner? I mean, they seem like they're from different planets, right? But they share a common, absolutely critical piece of engineering that makes both of them work. And the answer is a very, very special type of bearing. So, what is a bearing really? Well, at its core, it does two absolutely crucial things. First, it constrains motion, which basically means it forces parts to move only in the way they're supposed to. Think of a wheel spinning perfectly on its axle, not wobbling all over the place. And second, it dramatically reduces friction. You can think of it as the ultimate peacemaker between surfaces that would otherwise just tear each other apart. So here's the game plan. First, we'll uncover this unseen world that these components live in. Then, we'll decode the big choice every bearing has to make. Does it slide, push, or roll? After that, we're going to zoom way in to the microscopic art of surface science. And finally, we'll see how it all comes together to literally make our world go round. Right, so from the turbochargers screaming away in a diesel engine to the enormous gears in a wind turbine, bearings are these invisible workhorses. They are operating under incredible stress, extreme temperatures, and just mind-boggling speeds, all while quietly making sure our complex machinery runs smoothly, efficiently, and most importantly, reliably. Okay, the world of bearings can seem super complex, but it really all boils down to three fundamental actions. See, every bearing is designed to handle forces and motion in one of three ways. They either let parts slide past each other, they resist a direct push, or they allow them to roll. First up, you've got journal bearings. These allow for pure sliding motion. Just imagine a spinning shaft that's literally floating on a super thin film of oil. Then you have thrust bearings. These guys are built specifically to take a direct push right along a shaft's axis. And finally, the ones you probably picture in your head, rolling element bearings. Think about putting marbles under a heavy box to move it. That's the idea. They replace all that sliding friction with way more efficient rolling friction. So let's talk about that sliding family. Journal bearings are absolute masters of something called hydrodynamic lubrication. Now, they do have a bit more friction than a rolling bearing, but their superpower is their ability to handle just immense shock loads. That's why you find them as crankshaft bearings, taking an absolute beating inside a diesel engine, and as these really sophisticated floating ring bearings inside high-speed turbochargers. Now for the push family, or thrust bearings. These are designed for one thing and one thing only, handling massive axial loads. Some of them, like hydrostatic bearings, actually use pressurized oil to physically float the load. Others use these really clever tilting pads that create a dynamic wedge of oil to support all that force. And in some really high-tech stuff, you might even find bearings that use magnetic fluids to get the job done. Wild. And finally, we have the artists of the roll. Rolling element bearings are what most of us picture, right? Little balls or rollers spinning in a race. Their whole deal is a simple trade-off. They give you incredibly low friction and amazing precision, but they can be a bit more sensitive to shock damage compared to a journal bearing. We see them everywhere, from angular contact bearings that handle combined loads to full ceramic bearings that can operate in conditions where steel would just instantly fail. But you know what? The shape of the bearing is only half the story. To really get what's going on with modern bearings, we have to zoom in. I mean, way in. Because the true innovation, the real magic, happens at the microscopic level, in the science of the bearing's surface. See, when you're dealing with immense loads, crazy high speeds, or corrosive environments, a perfectly smooth surface just isn't going to cut it. Metal would crash into metal, heat would build up, and failure would be, well, catastrophic. So engineers had to get creative. They started designing surfaces that weren't just smooth, but smart. It turns out, engineers manipulate three key things here. First is surface texture. They actually add microscopic grooves and dimples. These aren't defects, they're features designed to channel lubricant and carry the load. Then there's material science. We're talking everything from advanced polymers to ultra-hard ceramics to get specific properties like wear resistance. And finally, lubrication.
And get this, it's not always oil. In some of these incredible designs, the lubricant can be water, gas, or even just plain air. All right, so let's connect all this incredible science to the actual machines that power our lives. This is where we see the real-world impact of these tiny, perfect surfaces. So deep inside every massive diesel engine, there are specialized journal bearings on the crankshaft that are constantly absorbing the explosive force of combustion. Their multi-layered alloy construction and those precise little oil grooves are literally the only things preventing the engine from seizing into a solid block of metal. Next time you see a wind turbine, look up. Massive rolling element bearings are what allow the blades to pitch and catch the wind perfectly, while another giant bearing lets the entire housing yaw to face into the wind. These things have to withstand decades of immense, constantly changing loads. It's just incredible. Okay, how in the world do you support a multi-ton propeller shaft on a massive ship? Well, you use a specialized stern bearing made of advanced polymers. And what's amazing is that these are often water lubricated. They use the very same seawater the ship is sailing in to reduce friction. How cool is that? And now we're back to our medical scanner. The reason a CT machine can create those amazingly detailed images is because its X-ray tube spins at unbelievably high speeds. And this is only possible because of a liquid metal journal bearing with microscopic herringbone grooves etched right onto its surface. That's what guarantees a perfectly stable, vibration-free rotation. And what about that hydro generator from the beginning? The entire weight of the massive spinning turbine, plus the crushing downward force of the water, all rests on a single colossal thrust bearing. Its tilting pads create this powerful film of oil that supports thousands of tons, letting it spin freely to generate clean energy for all of us. So from the microscopic grooves on a surface to the massive components holding up a power plant, bearings are just this incredible testament to human ingenuity. They really are the silent, hidden enablers of our mechanical world. So the next time you see something spinning, ask yourself, what marvel of engineering is tucked away inside, quietly fighting friction? Now that you know about them, what hidden engineering will you see moving the world tomorrow?